Our FD RX7 project car has been a long time in the making. Our last episode we got the Adaptronic modular ECU configured and we got to fire the car up for the first time. Always a milestone in any project build, but today is the more exciting part. We're on our mainline Pro Hub dyno and we're actually going to perform some tuning. So that's what we're going to cover in this episode, and tuning rotary engines is one of those areas that seems to be shrouded in mystery. There's so much misinformation out there, so many myths, and I think it's another one of those areas where people kind of expect that tuning a rotary engine is some kind of black magic. Good news, there's no magic. It is just tuning, but no surprise, piston engines and rotary engines are different, and this does require a few considerations with our tuning. So we're going to go over some of that as we go through this episode. Just a bit of a recap though, for those who are new to this project, I'll just cover what we've got here. This is a Series 7 FD RX7. It's fitted with a completely stock low kilometre 13B engine, so internally 100% standard. That's going to be a sticking point for us because the reliability of that stock engine will really limit how far we can push things. To make a little bit more power than stock though, we've got a turblown turbo kit. This consists of a stainless investment cast exhaust manifold and a Borg-Warner AFR 8474 turbo. That's also accompanied by a V-mount intercooler and radiator setup and some plumbing from Vinifab, and we've got a complete fuel system upgrade from CJ Motorsports, including a set of injector dynamics, ID 1050X primaries and ID 1700 secondaries, all being controlled by that Adaptronic modular ECU. Let's jump in the car and we'll talk about some rotary specific tuning considerations. Despite the fact that the piston and rotary engines work on completely different operating principles, interestingly, when we are on the dyno, the rotary engine actually responds in much the same way to fuel and ignition timing compared to a comparable piston engine. There are a few caveats to that though. First of all, with the rotary engine, we need to typically choose richer air-fuel ratio targets compared to a comparable powered piston engine. So let's dive into our Adaptronic modular software here at Eugene, and we'll have a quick look at the fueling side of things. We're going to come back and revisit this in a little bit more detail, but this is our main fuel table. We've got that displayed graphically up the top, and then we've got it numerically down the bottom. This is a volumetric efficiency based fuel model, or ECU, which means that it works in conjunction with a target air fuel ratio table and some other information that tells the ECU the size of the injectors. We don't need to get too deep into that, but if we head across to our target air fuel ratio table, we'll have a quick look at the targets we are running. So we're looking here at a three-dimensional table. We've got our inlet manifold pressure on the load axis and we've got our RPM on the horizontal axis. The point here, 100 kPa, this is our atmospheric pressure. So a couple of things we want to take away from this. Again, we need to run the engine a little bit richer than we'd run a comparable piston engine. One of the things we do also notice here in the idle area, generally we need to run a rotary engine a little bit richer than stock. With most piston engines, particularly with stock cams, we can get a really nice idle quality at an air fuel ratio target of 14.7 to 1. Rotaries we're generally going to run a little bit richer than this. They're going to get a nice, more stable idle if we're a little bit richer. So we're 13.5 to 1 here. Given that this is a street engine, we still want some reasonable economy, so I am still targeting in this area 2,500 to 3,500 RPM, 14.7 to 1, our stoic air fuel ratio. So this is going to give us good fuel economy. The downside with running leaner like this with a rotary engine, well, for that matter, any engine, is that it does result in more exhaust gas temperature, and we need to manage that. And for this reason, we can see that out in the higher RPM vacuum area. So here we're basically off the throttle, maybe on a transition through a gear shift or a lift off the throttle. We're not so interested in economy out at this point because it generally is going to mean we're pushing the engine quite hard. So you can see I've richened my target here to 14.0, and what this does is uses a little bit of additional fuel there to just help cool and control the combustion temperatures. What we're really interested in though is what's happening at higher boost levels once we get into the boost up into load. So at this point the engine is fitted with two Turbo Smart wastegates, external wastegates, and we're fitted with springs there that get us to around about the 15 psi 200 kPa mark. So we can see here that my air fuel ratio target at that point is 11.2 to 1. Now, if I was tuning a piston engine, I'd probably be quite happy to be somewhere between about 11.8 and maybe 12.2 to 1 at that similar sort of boost level. So we're already moving significantly richer. And as we move from 100 kPa down to our 200 kPa target boost, we can see that we are quite a lot richer again in all of those areas than what I would normally run a piston engine. As we increase the boost pressure, the load, we start running a richer mixture. We get down to 240 kPa there, we've gone a little bit richer again. 240 kPa, around about 20 psi of positive boost, and we're now in the 10 to 1 vicinity. Now, one of the areas we do have a lot of debate and a lot of arguments, I guess you could say, is in the air fuel ratio targets. And the problem we need to understand is everyone has their own ideas on what is going to work for a rotary engine. We hear a lot of people running in the mid to low 10 to 1 vicinity, and in my opinion, and with a few exceptions, that's probably a lot richer than we normally need to run. Does come down to our application though. For a street engine, we're going to be a little bit limited in how much time we can spend under wide open throttle if we value our license. On the other hand, if I was tuning an engine purely for circuit racing, where it's going to be under wide open throttle use for extended periods of time, then yes, under those circumstances, it could pay to move a little bit richer. It's all about understanding the application and the implications of our choices there. In our case, we're fortunate as well because we do have exhaust gas temperature sensors fitted to the exhaust runners pre-turbo on each rotor, so we can actually see what our exhaust temperatures are doing, and this can help drive our decisions on our air fuel ratio targets, because as we lean out the air fuel ratio towards stoic, our exhaust gas temperature will start to climb. With the rotary engine, we do get to a situation where at higher boost pressures we do need to sacrifice a little bit of power for a safe, rich air fuel ratio. And we will find that, for example, if we, even at the 200 kPa mark we're running here at 11.2 to 1, if we run this engine at 11.2 to 1 and then we leaned it out to, let's say, 11.5 to 1, at that point we will pick up some power. We're sort of at the point in our air fuel ratio where as we go richer we're starting to see the power fall off a bit of a cliff. So we want to be right on that point where our air fuel ratio is just starting to affect our power and we're starting to see that drop away. We don't want to be at the point where our air fuel ratio is giving us maximum power. It's going to be too lean and you're likely to end up seeing long-term engine damage. So we're sacrificing a little bit of power for more reliability is the order of the day. So that's our first topic there. Our air fuel ratio targets, rotary engines, they're going to be richer. The second topic that I want to talk about here is our ignition timing and our ignition control. In my opinion, this is probably the area where the most damage can easily be done to a rotary engine. Rotary engines are very intolerant of knock or detonation, which is an abnormal type of combustion. We get this in both piston and rotary engines. Piston engines, though, can be tolerant to light levels of detonation, and what this means is that when we're tuning the engine on the dyno, we can actually listen for audible knock, and we can run the engine right up to the knock threshold, and then we can stop, back the timing off to give us a safety margin. Trying to do this on a rotary engine is almost inevitably going to end up in an expensive engine failure, so we don't want to do that, and being conservative with the timing is the order of the day. I'm going to have a demonstration on the dyno and just see how the ignition timing affects our torque and our power shortly. The other aspect with the rotary engine which is really unique is that they run 2 spark plugs per rotor housing. They have a leading plug and a trailing plug. And again, a lot of confusion about how this works and what we're trying to achieve. Let's start by diving into our Adaptronic software. We'll actually see how this is dealt with inside of the tuning software. So what we need to do is go across to our main ignition table, and that's what we've got here. We've got that table being displayed graphically up the top, and again, a 3-dimensional table at the bottom. We've got inlet manifold pressure as our load axis, and we've of course got RPM as our horizontal axis. So the numbers in this table, this defines the ignition timing, or whereabouts the ignition event will occur on the leading plug. So that's the key there. This table responds, or corresponds I should say, to our leading spark plug. Then our trailing plug is controlled with a separate map, which we can find up here. This is called spark split in the Adaptronic. It's going to be different for different ECUs, but that's what our table is here. Now you can see straight away a much smaller table, much less resolution, and a lot fewer breakpoints because we simply don't need them. Now we've got the same axes though, manifold pressure versus RPM, and what this does is it defines how far after the leading plug has fired the trailing plug will fire. So the number of eccentric shaft degrees of rotation after the leading plug. So what do we do with this table? And again, this is an area that we can see a lot of confusion and misinformation. In the earlier days where we didn't have so many ECUs that were designed for controlling rotary engines, it wasn't uncommon, definitely frowned upon, but it wasn't uncommon to actually fire the leading and the trailing plug together. We don't really want to do that. Before we dive into this table in a bit more detail, let's talk about why that trailing plug is there, what it does do and what it doesn't do. There's a lot of people think that we're going to pick up a massive amount of power by messing around with our trailing split table. The reality is it's simply not going to happen. Yes, there can be some small gains, but they will be exactly that, small gains. If we look at the research, generally it's understood that around about 95% of the combustion process is completed by the leading plug. So that's really our key plug there, the one that's the most important. And if we actually unplug the trailing ignition system completely, unplug the coils for the trailing plugs, and we do a dyno run, you're going to actually see you don't miss out on much power, even with no trailing plug firing at all. So trying to chase power with our trailing split, it's just not going to be a good idea. What the trailing plug does is it does help complete that combustion process, burning off any remaining fuel and air that's still in the rotor housing. So this is a little bit about power, but it's actually a lot to do with emissions, which is something that the rotary engine generally struggles with. So with that in mind, what are we going to be doing with this table? Well, what we'll actually find is if we look at an Adaptronic base map, that entire table is fixed at a set value of 10 degrees, and to be honest, that's probably going to be absolutely fine, and it's certainly going to be safe. Alternatively, we can look at what Mazda do with their own trailing split tables. There's a lot of resources out there on the internet where people have reverse engineered those tables, and what we've got here is something that's sort of a bit of a hybrid. What we can see is that in the idle area, we've increased that split to 15 degrees, and this is generally what Mazda run in the idle areas, a 15-degree split between leading and trailing. In the cruise and vacuum areas, we are at 10 degrees, and then in the higher boost areas, I've just reduced that split a couple of degrees there to 8. Now, what we need to understand is the effect of reducing that trailing split. So as we reduce this, it sort of has the same effect as overall advancing the timing, so care is needed. So I've reduced that there by 2 degrees. I would not suggest going any further than that, but there can be some small improvements to be had by reducing that split slightly. So again, we can pretty much take a table like this that's developed and proven. We can use this in just about any engine we are tuning. Again, it's not the place to be trying to gain big improvements in our power. To see how this works out, what we're going to do is start the engine up, get it running, and we'll do a demonstration on the dyno. All right, we've got ourselves up and running here, and what I've done is I've got into the middle of this particular cell here, so 3000 RPM and 50 kPa, and we've got 10 degree split in there at the moment. So I just want to modify that split, and we'll have a look at the effect on our power and torque. Now it's actually easier to monitor this if we look at our torque. The torque, of course, is what's being measured by the dyno, and the power is then calculated from the torque. So essentially the torque, if that goes up, by definition the power also will go up at the same RPM point. So let's have a look over at our dyno, and we've got our torque being measured here, our rear torque, both a gauge as well as a numerical value. We can see we're sitting at around about 130 pound-foot at the moment. It's actually easier though, in my opinion, to use this red line that we've got down here. So this red line shows the torque in real time, so we can see it changing. So what I'm going to do, let's come back across to the laptop screen, and we're going to start by reducing that split. So let's take our split from 10 degrees to 15. Now I haven't pressed enter yet, so that change hasn't taken effect. I'll just make sure we are in the center of that cell, and we'll make sure we're stable. Okay, we'll just wait for that torque to stabilize, so we can see it's sitting there just about on the cursor, which I'll move. And what we'll do is we'll press enter. We we can see that the torque line really hasn't moved at all. So we've gone from 10 to 15 degrees, no effect. Let's advance our trailing timing, so we'll reduce that split down to 5 degrees again, looking for that stable line on our graph. Haven't pressed enter yet. We'll press enter and look at the line, and again, we really don't see any significant change. So just to show you there that the effect of our trailing split, we're not going to see massive changes in our power, and it's not the place that we want to spend the majority of our efforts when we're on the dyno. Just remember, advancing the trailing timing, or reducing the trailing split, has the effect, I should say, of advancing the trailing timing, and this can be dangerous. So numbers that are too small in that table can potentially be dangerous. If in doubt, and across the board 10 degrees, that's going to be a pretty good, safe starting place. All right, so we've talked about our trailing split, but let's go back a little bit and we'll have a look at our main ignition map, which we've already glanced at there. So this is the bit that scares off most tuners when they're getting involved with rotary tuning. What do we do with these numbers? Well, there's a few ways we can deal with this. There are a few ECU manufacturers out there that come with pretty good base maps for the rotary engine. The Adaptronic is no different here. We've got base maps for a variety of different rotary engines, so that's a pretty good place to start, at least seeing what Adaptronic have found to be a safe starting point. Alternatively, just like the trailing split table, there are a lot of resources out there on the internet now that show the sort of timing numbers that Mazda were using. So we can kind of reverse engineer those, have a look at what those are doing at certain boost levels, and then basically apply those to our own tuning. Again, if Mazda found these to be safe, understandably, that's going to be a pretty safe starting point. However, what we really want to do is be able to figure this out for ourselves and see what the rotary engine actually wants. If we understand that, then we don't need to rely on others. We don't need to rely on a base map, and we can optimize the map to suit. So what we're going to do is go through what's called a torque optimization test here on our mainline dyno. So we'll get our engine up and running again. First of all, let's have a look at our ignition table, and again I'm trying to basically run the engine at that same point we were just looking at, basically 50 kPa, and actually we'll come up to a little bit to about 55 kPa, and we are at 3000 RPM. So what I've done here is I've highlighted the cells surrounding that cell, and that means that during this test that we're going to do, our results won't be affected by interpolation. Let's have a look over at our dyno screen and we'll see what we've got there. And what we've got on the vertical axis is the torque being measured by the dyno in pound-foot. On the horizontal axis, we've got the ignition timing being sent across from the mainline dyno, from the Adaptronic to the mainline dyno via CAN communication. So what this is going to do is plot the relationship between engine torque and our ignition timing. Now, while I've been talking there, we've been under steady state conditions. So I just want to first of all point out, I've got this particular channel here. It's listed as 0 to 5 volt external 1. This is an external input, which is actually a thermocouple amplifier. So this is one of our EGT channels. We can see that it's sitting at about 825 degrees C. Given that we're in vacuum here, there's not a lot of load on the engine. I'm barely touching the throttle. It's quite hot, a lot hotter than we would see with a comparable piston engine. This is why the air-fuel ratio that we choose is so important. But what we're going to do now is we're going to start by setting all of those cells to 10 degrees. So we've retarded the timing dramatically. Before I get this test started, look what's happening to our exhaust gas temperature. It's skyrocketing. It's going all the way up through 900 degrees, and it will continue to climb for a while. So this can be quite dangerous if our EGT gets too high. This is because the combustion event is now happening very late in the rotor cycle. All right, what we'll do is we'll clear our test over here on our mainline dyno, and we'll click begin. And what I'm going to do now is advance the timing at a degree every second, trying really hard to stay as stable as we can on our throttle so that our torque is going to only be affected by our ignition timing. So we can see that we're getting a nice little red line being drawn here on our dyno screen, that relationship between our torque and our ignition timing. So let's carry on. Now we're going to go through all the way here to 45 degrees so we get a really good look at how that torque curve looks versus our ignition timing. We've got to 45 45 degrees there, so I'm just going to back off the throttle and let's talk about our results. Now, first of all, while we're waiting for the dyno to slow down here, you're probably thinking, are you crazy? 45 degrees of ignition timing, aren't you worried about knock? What we need to understand here is because we are under vacuum, we're a very light load and I'm barely touching the throttle. There isn't a lot of load on the engine. So under these conditions, very unlikely to get to a condition where knock will occur. That's why I chose that point. I'm not crazy and I don't want to damage our 13B engine. Now let's have a look at our results there. So this is the curve that we've got. Just ignore the part where our red line drops back down. This is simply where I got off the throttle. So at the start of our test, we can see here, we had around about 105 pound-foot of torque. The dyno is actually drawn in a crosshairs here showing us MBT. So this is a term you may have heard of when referring to piston engines. It's no different in a rotary engine. This is simply the point in the engine cycle where if we set our ignition timing to MBT, this is where getting maximum torque being produced inside the combustion chamber at a point where it can have maximum mechanical advantage, trying to rotate that rotor, which in turn rotates the eccentric shaft, which is what creates torque and power. So the dyno has shown us that that particular point there for that operating cell is actually 30.8 degrees. Let's call it 31 degrees, and it's given us 152 pound-foot of torque. So by optimizing our ignition timing, we've picked up 50 pound-foot of torque, give or take, around about 50%. So it's not insignificant, and this is why it's important to optimize our ignition timing. However, the other aspect that I mentioned, we do need to understand the effect on our exhaust gas temperature. We saw our exhaust gas temperature skyrocket when our ignition timing was very retarded. And this is something we need to be mindful of. If you're setting your ignition timing very conservative because you think you're safeguarding your engine, yes, it's going to probably make the engine unlikely to suffer from knock. You will be giving up a fair watt of power and torque, but you can also end up with excessive EGT. So we have to find the happy sort of medium, somewhere between a retarded safe ignition timing that's going to create skyrocketing high EGTs and something where we're making good power and torque, but we aren't likely to suffer from knock. Now, the interesting thing with the rotary engine is that the MBT curve that we've just looked at, the relationship between torque and ignition timing, this is much flatter than what we normally see for a piston engine. And we can see there that all things being equal, from around about 24 degrees of ignition advance all the way through to 45 degrees of ignition advance, we've only seen our torque vary by probably 3 or 4 pound-foot of torque. So what we want to do is definitely take advantage of this initial increase in our torque as we went from 10 through to about 20 degrees. From 20 degrees though to about 30 degrees, we've seen an increase, but not a significant one. So what we're looking at when we are tuning the ignition timing, we're trying to be somewhere to the left of MBT. So where we've still got a little bit of potential to improve the power and torque with adding timing. We've still got plenty of timing in there, so we're not creating very high EGTs. So basically at the point where we first start to see the torque flatten off, we don't start to see those such significant gains in power and torque as we advance the timing. That's about the time to take stock of things, leave our timing there, don't chase that last horsepower or last few horsepower from your tune. Be comfortable there that you've got a safe and conservative timing with a margin that's going to give us a engine that's unlikely to suffer from knock. That's one way to keep your rotary engine together. Now that we've talked about some of the differences in how we need to approach our tuning with the rotary engine, we can look at the actual process we're using, and here this is essentially identical to how we tune a piston engine. People get worried about tuning any engine for that matter because they think that without a base map or a start file, they're going to damage the engine getting up and running. Well, when we are tuning, what we're actually going to be doing is working from very low in the load and RPM initially, and we're going to be building up a picture of both the fuel and ignition tables under these conditions, and then we're going to extrapolate those trends out into the untuned areas. If we jump across to the fuel table for a second, we can see that graphically, if we look at that table, with very few exceptions, it's relatively smooth. So if we start at low RPM and low load, and we build up both the RPM and load, we can start extrapolating the shape of that curve out into the higher load and higher RPM areas, meaning that when we do get into those areas, we're already going to be really close, meaning that it's unlikely that we're going to do any damage to our engine. What we'll do is just do a quick demonstration here of our steady state tuning process. So what we're going to do is get our engine running, and we'll come up to 3000 RPM here and have a look at what we actually need to do. So when we first get into an area, an RPM range that we haven't tuned before, we're going to be starting with our throttle as close to close as we can get to. This allows us in this case to get down to our 40 kPa cell. And of course, we've got a pretty well tuned engine at the moment, but just looking at our air fuel ratio, we can see that our measured air fuel ratio is sitting at about 14.3 to 14.5 to 1. It's moving around a little bit, but that's pretty typical. The target air fuel ratio, which is what's directly below that, is what we're aiming for. And you can see that at the moment we're running a little richer than our target. So just using the page down key there, I can just remove a little bit of fuel and move us onto our target. You can see it's as easy as that. Once we've tuned that particular cell, we can now increase our throttle opening a little bit. We'll come down to our 50 kPa cell. The dyno's just going to apply a little bit more load in order to maintain that same engine RPM. Looking at our fueling there, we can see that we're sitting at around about 14.8, maybe jumping up to 15 to 1. So what I'll do is add a little bit of fuel to that cell, and we can get our fueling dialed in. The process of adjusting our fueling in steady state conditions is just a rinse and repeat of exactly that. We're just going to move through from as low on the RPM as we can, as low on the throttle. We're going to increase our throttle until we are at wide open throttle, tuning a complete column of this table. Once we've done that, we can copy and paste that column out to the next highest RPM range, and we're going to repeat that. And again, just tuning ahead and extrapolating like this means that our tuning is really safe. Now what we're going to do is perform a ramp run, and this is obviously the exciting part of the tuning process. So let's head back over to our dyno screen and we'll get our engine up and running for a ramp run. Right, our run complete there, and we'll just let our dyno come back down to a stop, and we can see at this point 393.3 horsepower. If you prefer to work in kilowatts, 293 kilowatts at the rear wheels. And looking at the data that's on our dyno screen there, we can see that the top line there, our red line, is our boost pressure. We can see that's just getting up to that 200 kPa zone. We've got our air fuel ratio. This time I'm actually displaying this in lambda just to be a little bit confusing there, considering everything else we've looked at is in air fuel ratio units. But essentially all we need to know there is I've got a reference line here, this dotted line. That's what I want to be running once I'm at my 200 kPa target. So we can see at a glance during the dyno run how close we are to that. We can see that our line is sitting really nice and close to that. 393 horsepower, pretty good result for what is relatively modest boost pressure there. Now, I've talked about the fact that our air fuel ratio does affect our power and torque, and we're at a point where with a rotary engine we really don't want to be trying to lean the air fuel ratio up to the point we're making maximum power. So what we'll do is just a quick test here. Let's go back to our fuel tuning. We'll go to our air fuel ratio target, and let's select our 200 kPa row there, and let's change our air fuel ratio targets from 11.2 to 11.5. Because this is a volumetric efficiency based ECU, that's all I need to do when I want to change my air fuel ratio targets, and the ECU will do the heavy lifting in the background. So what we'll do is we'll save our run there on the dyno screen so that it'll actually stay up live, and what we'll do is we'll call this 11.2 to 1. That way we'll be able to reference it later. Now that's going to stay up as I've said, so we'll be able to overlay directly on top of this. So let's do another run and we'll see the effect of leaning our air fuel ratio out there. Right, our second test there complete. We can see 399.4 horsepower, pretty close to that magic 400 horsepower at the wheel mark. We can see our red line on our dyno plot there for our air fuel ratio. It's pretty much done exactly what I had asked. We've still got a bit of a rich spot here as we come onto full boost, but essentially it's done exactly what we asked. So we've picked up around about 7 horsepower, 6.5 horsepower thereabouts from leaning our air fuel ratio out. So this is what I'm getting at here. Definitely there's more power to be had by leaning our air fuel ratio out, but the problem is that combustion temperatures, exhaust gas temperatures are going to skyrocket. It might be fine for a single pull here on the dyno, but under sustained wide open throttle operation, you're likely to end up damaging the engine. So we do need to err a little bit on the side of safety. So there's some insight into some of the more common questions I get about rotary engine tuning. Of course, we haven't been able to do justice to every potential question there is about rotary tuning, but these are some of the core ones, and hopefully the dyno demonstrations also have helped really reinforce the understanding of how those concepts work. Now, for those of you who are interested in learning more about rotary tuning, that's actually why we have this FD3S project car, and I've just finished filming a full worked example on the Adaptronic ECU for the rotary engine that's going to be added into our practical standalone tuning course. And the idea behind this is it's a walkthrough, an informal walkthrough of the HPA 10-step tuning process that you can watch from start to finish, and you'll learn the entire tuning process. Now, this is useful for anyone who wants to learn to tune the rotary engine. Obviously, we have presented it on the Adaptronic ECU platform, but all of the concepts really cross over to just about any standalone ECU that supports rotary engines. I just want to quickly take you through that course so you can see how it's laid out. So head across to the laptop screen. This is the course. It's broken down into individual video modules, making it really easy to come back and review a specific topic at a later point. The course is generic, so it's applicable to tuning now rotary or piston engines on any standalone ECU. And what we present, the key part of the course, is this HPA 10-step process. So by following this through, each of the individual steps of that process is quick and easy to complete, and at the end of that 10-step process you've got a completely tuned engine offering great power, great torque, and most importantly, great engine reliability. If we scroll down through here, each of those 10 steps being explained there, and a few modules in each of those that goes into detail on what that step includes. We've also got a set of modules here that covers road tuning, how to tune without a dyno. While the course is presented using our mainline dyno, we know a lot of our customers come from cities and even countries where there are no local dynos. We'll show you how to get the best results if you can't get onto a dyno. We've also got some modules in here that cover some of the intricacies of tuning turbocharged engines. For our FD3S worked example, we're actually doing that anyway. And then we've got our worked example library. So right now this includes the ECU Master EMU Black, we've got the Megasquirt MS3 Pro, we've got the Cyvex S8, the Haltech Elite 2500, the Motec M150, we've got the AEM Infinity, and we've got a couple of worked examples here on the Link G4 Plus, both in traditional and modeled fuel equation. So the worked example we're going to be adding in here, it's going to go right down here at the bottom, and hopefully by the time you are watching this episode, that's already going to be available. We'll put a link that you can follow if you want to learn more. If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.